kilograms, right? Initially at rest, it's on a horizontal surface, which means there's no angles involved. This requires a 75 Newton horizontal force to set it in motion. So in order for it to begin to move, it has to overcome 75 newtons of horizontal force. That makes this a static friction. However, after the crate is in motion, a horizontal force of 60 newtons is required to keep it moving with a constant speed. So now, once we've got it to move, it's going to take a lot less force to keep it moving. And so this would be known as the kinetic friction. Find the coefficients of static and kinetic friction between the crate and the floor. So we're not going to go ahead and look up the values for these. We're going to actually get them mathematically, theoretically from the formula. So recall that static friction, by definition, is going to be mu static times the normal. Now, if we go ahead and we divide, because we want the mu s by itself, we divide both sides with the normal, we get that mu s, which is the coefficient, is the static friction divided by the normal. We know the static friction is 75 newtons. However, what is the normal? Now, when we say normal, again, we're making reference to what we discussed in great detail in the third law lecture video. So if you're not quite sure what the normal is, what the normal force is, I would refer you to the third law video. Okay? So we need the normal force. The normal force, when there is no angle, okay, in other words, if I have something flat on the ground, the normal force is going to equal to the weight. In other words, if I have the weight going down, I have the normal force going up. And this would be first law in this case, right? Going up and down. So there's an opposite and equal reaction based on third law as well. The weight would be the normal force. Well, what was the weight? Weight is equal to mass times gravity. That's 20 kilograms times a 9.8 meter per second squared. It looks like 196 newtons. Notice how the newtons cancel out. And they should cancel out because this coefficient of friction has to be unitless. So in this case, we're going to go ahead and get a value of 0.38. In this case, we're going to use the 60 newtons for the kinetic friction. If you know anything about what I've taught you so far about the coefficients, is you would totally expect that the coefficient of static friction should be bigger than the coefficient of kinetic friction. When you put this in a calculator, you're going to get 0.31. And that's true, right? We totally expect the static friction, to be greater than or equal to the kinetic friction. Or in other words, like we said previously, mu s should be greater than or equal to mu k. Again, notice there are no units because this is a coefficient. Do not confuse the force of friction with the coefficient of friction. Coefficients do not have units. Mutant Pumpkin. 230 kilogram pumpkin is pushed horizontally with a force of 700 newtons. If the coefficient of friction is 0.2, calculate the acceleration of the pumpkin. I'm going to pick this way positive and this way negative. Something subtle that maybe you've noticed, I put a K here. The K is going to be for kinetic, just to keep that in mind. We do have forces on the y-axis and on the x-axis. Let's go ahead and set up along the x-axis, okay? Along the x-axis, we would have second law. We would not have a second law for the y-axis because it is not accelerating up and down. The acceleration is going left and right. So I have two forces. I have a positive force, F, capital F, and a minus kinetic friction going to the left. I think something that would be wise to do at this point would be before we start plugging numbers in, let's go ahead and solve for A by itself. Let's get A by itself. Divide both sides by M. The entire thing by M, by the way, the entire thing. I get acceleration is big F minus friction divided by M. They gave us a mu. The mu is 0.2, so I'm going to go ahead and put that in. Right, there's that mu right there, 0.2. What's the normal force going to be in this problem? Just like before, the normal force will be equal to the weight. What is the weight equal to? You know they gave you the mass, right? Recall, the normal force equals the weight. That's 249.2 kilogram meter per second squared over 230 kilograms. The kilograms cancel out. It is the correct unit for acceleration, meter per second squared. And putting this in the calculator, I get acceleration is 1.08 meters per second squared. That's a pretty believable number. It's a pumpkin, by the way. For your summary, I want you to explain how friction is mathematically used in these problems. Explain how friction is mathematically used in these problems. Problem 7, Revenge of the Dock Worker. Boom, boom, boom. So this should sound familiar. We just did it like a few minutes ago. Remember, initially at rest, okay, and it requires 75 newtons to move it, right? This is your static friction. However, after the crate is in motion, this much is required to go ahead and keep it going. This time they gave us one coefficient. This is static. You'll notice that this time they did not give us the mass, right? A, calculate the weight of the crate. So if you thought weight is mass times gravity, that's great. We have gravity, but we don't have mass. We're missing this and we're missing this. So that doesn't work. You're thinking, well, let's set up Newton's second law. Well, the problem is if you're going to use this number and this number, you can't because it hasn't been set in motion yet. That's static. That'd be first law. So you could do first law, but the problem is you don't even know how much force you're applying, so you can't even do first law. Sad face. Do you recall the normal? What is the normal equal to? Because if I write the equation for friction like that, but then I go ahead and I'm solving for the normal force, that's the normal force though. We're asking for the weight. So how can we justify that the normal force is the weight? Well, you would recall from the previous problems that we're going to make the claim that as long as an object is sitting flat on a surface, according to Newton's first law, the normal force would be identical to the weight. So if the normal force is 166.67 newtons, then therefore the weight would be 166.67 newtons. So the weight of this box, of this crate, is 166.67 newtons. If weight is equal to mass times gravity, and I want to get the mass by itself, I would divide both of them by gravity. So the weight was 166.67 newtons. Divide that by gravity. We're going to get about 17 kilograms for the mass. You know that Fk is equal to mu k times normal. If I want the coefficient, that's the mu. So I would divide both sides by the normal. Mu k is Fk over normal. The kinetic friction was 60 newtons. Remember, they didn't tell you in the problem, this is kinetic friction, right? They said this is the force that needs to, the friction force that needs to be overcome in order for it to keep it going with a constant speed. That's another way to say kinetic friction. If I divide these two, I'm going to go ahead and get 0.36. Recall, again, the units are going to cancel out. Coefficient should be unitless. Unitless means there are no letters at the end. This is very important because a lot of you have in your worksheets, you've been giving me answers without units. This time, you actually need to give me some answers without units, right? If it's a coefficient, there will be no units. If it's a force, it'll be friction. Mu s was 0.45. What we just got was that mu k is 0.36. So why does this answer make sense? It should make sense to you because mu s should be greater than or equal to mu k. In other words, this number right here, right, mu s, should be larger than 0.36. If we did this math and we got 0.45 or 46 or something from UK, that would be wrong because it's got to be smaller than. Very rarely is it equal to it. For your summary, please talk about how the normal force is useful when doing problems that require friction. And that's it for this video and these notes. We are done with Newton's laws. Yay.